Good morning, students. So today we are going to see one more concept, that is force on a differential element, current elements. So the heading of the topic is force on a differential current element. So we can see that for practically a differential elements of a charge is made up of a very large number of small and discrete charges. The volume thus occupied by these charges is obviously small, but it is effectively greater than the average separation between charges. The differential force on equation, we can write the equation for this is given as differential force equal to differential charge into the velocity of charge into the or cross product of the magnetic field. This is in terms of Newton. Okay. So when there is a movements of electrons in the conductor, we can consider any conductor in which the electrons are in motion, and along with these electrons in motion, the immobile positive ions form a crystalline array of structure. Means the positive ions will form the crystalline structure, and due to the motion of electrons, there is a shift in the crystalline, and for this crystalline there is a opposition force, that is Coulomb's force, that holds the crystallines in the aligned state. So this type of slight movements in the conductors is called as the Hall effect, or the voltage produced by those small voltages across that current conductor produces the Hall voltage, and this effect is called the Hall effect. So we have the formula or basic equation, that is dF equal to dq into V into B. For this we apply the differential force, and this is the differential charge. So from previous derivations we know about the current density, that equation. This you can give as the some equation number 1. Then for current density equation we have J equal to rho V into velocity of the charge. So this you can give as some equation number 2. But the differential elements of charge can be expressed in terms of voltage charge density. So dq also we can express in terms of the differential charge, that is dq differential charge can be given as rho V into dV. So these all equations we have studied in our previous derivations and all. So now substituting the value of dq, this value of dq, so this at the top, this is not a vector, sorry, this is not vector, this is this differential charge, vector is this, that is velocity. So substituting this equation in the 3 in 1, if I substitute 3 in 1, I am going to get as differential force diff equal to rho V into dV into velocity vector V cross product with B. Okay. Then expressing the dF in terms of JF using this equation number 2. So what I am going to get is, for dF, if I substitute in terms of current density, that is dF is equal to J cross B into dV. So this you can give as some equation number 4. So, but we have already studied the previous chapter, the relation between current elements, as we have current element relation as J dV equal to K ds, or in terms of current it is differential length, that is TL. So this is also an important relation, that is current density with the differential surface and differential length. Okay, so this is also an important relation. So then the force exerted on the surface current density is given by, so now the dF, we can write it as, dF is nothing but K into, or cross product with B into ds. So just substituting the one value in the other equation. So this becomes the equation number 5. So similarly, if you substitute for IDL, so what is the value we get to it? So dF is equal to IDL cross product with B. So this is the one more equation. This you can give as equation number 6. So now integrating equation number 4. Integrating equation number 4 on both the sides over the volume. Over the volume, if I integrate, I am going to get it as, so F is equal to force, it is integrating volume, so it is J cross B into dV. And integrating equation number 5, integrating equation number 5, where the K and B are present. So this F is equal to S, because we have the surface. This is over closed or open or closed surface. Okay, so it is K cross product with B into ds. This is the one more equation. So this equation you can write it as equation number 8. This is equation number 7. Okay. Then similarly, if you integrate with IDL, that may be equation number 6. So if I integrate with DL, integrating over closed path, that is where we have the length term. So that is F is equal to integrating length, that is I dl cross B. So this you can give as equation number 9. So we can see that the magnetic field developed by the current element to IDL does not exert a force on the element itself, similar to the point charge does not exert a force in itself. So the magnetic field B is always external to the current element IDL. So if a conductor is straight and the field B is uniform along it, then integrating equation number 6, we can get a simple equation, that is if conductor is straight, if the conductor is straight and field B is present, then if I integrate that equation number 6, that we will get as F is equal to direct I L cross product with B, and the magnitude of this value we can write it as force equal to I L B sin theta. Okay, so this equation we are going to get, that is the force. So this is about the simple topic, that is force on a differential current element, and we can solve some problems in the next video based on the formulas we get. So we will continue in the next class with some two problems. Okay, thank you.